till now we have seen the subsystem level of each and every the designed part. Now what we are going to see is that once we interface and connect our electrodes to the specific person to acquire our ECC signal, how the processing will be done, right, everything we will see. Now we will compare the signals, the outputs at at this point as well as at this point, right. We will see how accurate, how good the ECC signals that we get at these two outputs too, as well as at this point too. So in order to acquire the signal from the person or from the subject, the thing is that we have to connect 3 different electrodes. If you recall, we told that one electrode, one voltage source will be from right arm to the right leg, right. So another voltage source will be from left arm to the right leg, right. So this is one particular voltage source, this is another particular voltage source, and the signal strength or the signal amplitude of the from the this particular source as well as this particular source will be almost equal to the same. That is the reason we require to have a higher CMRR operational amplifier, and since we have to do the difference between the two voltage sources, we require to use some difference between the outputs. So in order to perform the difference, either we have to go with a differential amplifier or we will be going with an instrumentation amplifier, right. But differential amplifier cannot be used in this application, because the input given to the system, the output that we get from the subject will be all of common mode signal, and we require to have a higher CMRR value. So differential amplifier will always affect from CMRR, that is one thing, and the input impedance of our instrumentation amplifier is higher compared to the differential amplifier. So that is the reason we will be going with instrumentation amplifier, but the instrumentation amplifier that I am using here is INA 128. So you can look into the data sheet in order to understand the detailed architecture, detailed specifications of the instrumentation amplifier of INA 128, so that even you will get understand about the working, the gain setting, the resistance value that we choose and why we have chosen, right, everything we can see from the data sheet. Now when we see the output at this particular point, since it is not a processor signal, only the amplification stage that we have done, we can see raw ECC signal, amplified version of ECC signal. But as if you recall the discussion, so initially we have discussed as well as professor discussed in the class that the raw ECC signal will always prone to lot of interference due to so many noise due to other signals. So those are nothing but our power line interference, baseline wandering, right, motion artifacts, all those things will be observed at this point, right. So we will try to see the effect of the baseline wandering in the system. So if you recall, so the baseline wandering is nothing but the signal will be always wandering with respect to this baseline, right. This is due to because of the respiratory. So during the respiration of our breath, because of that it creates some kind of a noise into the system. So that will be somewhere around lesser than 0.5 Hz. So since we are using a high pass filter, so after passing through the high pass filter, so we can see the complete removal of our baseline wandering, and even motion artifacts will also be in the same range. So completely will be eliminated when we pass through this particular system, this particular system. Then we also have some odd multiples of our power line interference, so which is greater than 100 Hz. So by using our low pass filter we are completely eliminating it, and notch filter to remove our 50 Hz signal. And we will also see, since we have also seen in a practical as well as theoretically as well as the simulation version how exactly this works, right. So we will only show till this point, because this requires some more computational requirement in order to do verification. Since we are using DSO, digital signal oscilloscope, since whatever the signal are nothing but will be stored in terms of our digital outputs, even by using our DSO at this particular point we can easily analyze the BPM of the subject that we are connecting it, and subject that we are connecting to the input of our amplifier. Now we will try to see the outputs at each and every point. So starting from the output at instrumentation amplifier at this point, then connecting the output of the instrumentation amplifier to low pass filter and check the output at this point, connect the output of the low pass filter to the high pass filter, check the output at this point, and we will see how much difference in the amplified version as well as the elimination of a noise in the pre-processing stage, everything we can observe at this point too. So, in order to connect the electronic circuit to the subject, we require to have some electrodes. So, we are going to use some ECG patch electrodes which are available in the market. So, these are, let me take out the ECG patch electrodes. So, these are our ECG patch electrodes. So, these are our ECG patch electrodes, if you see that, right. So, these ECG patch electrodes will have a metal contact on top of it, and these are not reusable, use and throw. Once we use it, we have to throw it out, disposable ECG electrodes. So, we will be placing one at right arm, one at left arm, other one at right leg, because the reference is our right leg. So, when we see, we have already connected to the person. So, one we have connected to the right arm, other one we have connected to the left arm. So, it has a stickiness inside as well as silica gel too. So, here at the back side we can see the silica gel is to just to remove the impedance, to decrease the impedance value, and this is the at right leg position. So, this acts as our reference, right. Now, we will take ECG connectors. So, I am using some ECG connectors. So, these are our ECG connectors, sorry, right. So, 3 ECG connectors we are taking it. So, what I will do is that one I will connect it to the reference point, I will connect it to the leg, whereas one I will connect it to the right one, other one I will connect it to the left arm. So, I just made the connections even in the circuitry. So, at this point one we will connect it to the positive terminal, right, other one connect it to the negative terminal. So, when it comes to the breadboard, when you see the breadboard, so what I have done is the outputs of the ECC signal, right, through the leads connected to the inputs of both here the inputs of the both instrumentation amplifier, and this particular blue color trimmer pot which is of 200 ohms pot we are using, and set it at 100 ohms. So, that the gain will be as per the data sheet. You can calculate the gain of the system based upon the resistance that we have used, somewhere around 500 to 100,000 gain we are using it. So, let me switch on the power supply and we will see how exactly the signal will look like. So, what I will do is that I will connect. So, since our interest is to see the signal at the output of an instrumentation amplifier, so I will connect the output only to the instrumentation amplifier and remaining connections I will remove. So, I am connecting it to the output of instrumentation amplifier. Now, when I look into the oscilloscope, how the exact signal will be, we can see some signal we are getting it, but there is some offset. So, here we can see this is our ground point, but there is some offset, right. And when I increase the time duration, time scale, we can even see some kind of wandering, right. So, observe, started increasing the value, again it starts decreasing, again it starts increasing. So, like that it is a wandering. So, it is may not be clear in this way, but if I connect it to the low pass filter, so what I will do is that the output of the amplifier I will connect it to the low pass filter, so low pass filter, and the output of the low pass filter will be connected to the oscilloscope. Now, when I see the signal in the function in our oscilloscope, right, there is some shift from positive to negative. Now what I will do is that just let me auto scale once, right, and let me zoom. I will change the time duration to somewhere around 10 seconds, right. So we can see the wandering, we can clearly observe. So some part of the noise has been completely filtered when we pass through the low pass filter. So what I will do is that I will change, slightly shift the signal to down, little bit down, and I will increase the time duration. Right now one box is completely 1 volt, I will change to 500 for the increase of the amplitude. Keep it down. So suppose if I zoom it, time duration if I increase, one thing it is clear that we are getting some peaks and the pattern is also looks similar to that of your ECG, isn't it? See here the QRS, 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 QRS and P, QRS, somewhere here T and U. So T and U is very hard to visualize using this particular the patch electrodes, but if you have rather than 3 lead electrodes, if you go with the 12 lead electrodes, even that signal it is it is the pattern will be easy to recognize using that particular 12 lead electrodes. But we have some offset as well as we also have some kind of wandering in the signal. So in order to understand the wandering, so I change the time duration to somewhere around 50 seconds. It's too high, so I will take to 25 seconds. So in order to finish one box it takes 25 seconds. So 50 seconds to 2 boxes, 75 seconds, approximately 1 minute to 2 minutes if I wait, I can easy to understand how the signal will be looks like. But here it is clear that it is started wandering, right. So you can see sometime it is at the peak, sometime at the negative, right. This is because of our respiration rate or even because of our motion artifacts too. So basically because of the respiration while taking the recording, this creates some wandering in the system, right. In order to remove this noise, so we have to pass through high pass filter. Since we have not passed through the high pass filter, we can only see the signals which are always wandered with respect to the baseline. Now what I will do is that in order to even remove that as well as the motion artifacts, when you are moving there will be always noise generated into our system too. So if I want to remove everything, what we have to do is that we have to pass through the high pass filter too. So now I will connect the output of the low pass filter to the high pass filter. So I will remove this connection, connect it to the high pass filter, then the output. So output pin is somewhere around first pin here. So this is our output, I am connecting it here. When I look into the signal at oscilloscope, the offset is removed and you can see there is some sudden jump down. So to see that, what I will do is that first I will auto set it and I will change the right, I will change my the time duration, time scale to somewhere around 1 second or 2 seconds, and the box length, the amplitude. See the high pass filter whatever we design have the gain of 2. So that is the reason we can see the amplitude signal. So I will put it somewhere around 1 volt or 500 milli, then right. So when we look into the signal, it is continuously recording it. When you look into the signal, so we have different peaks. right. So here it is easy to understand QRS peak very easily, QRS and the amplitude of the QRS is more compared to the other peaks, isn't it? Right. When we observe, it is clear that the QRS peaks, it is easy to visualize using our system. Right. Clear. Now, how do we understand our BPM in this? So, if I want to understand, I have to calculate how many number of such peaks we are getting per particular time duration. So, to set that, what I will do is that since it is our digital oscilloscope, we can easily visualize one box is corresponds to how many seconds. So, we will see how many number of boxes we have, and we will take how many, we will calculate how many number of peaks that we are getting. That is one way. Another way is, if I put a cursor, if I find the frequency between one peak to the other peak. So, if I know the time duration, 1 divided by time duration, I automatically get the frequency. That gives me the what rate that peaks are even obtaining. So, what I will do is that either two, both the ways we can go ahead. So, first thing I will see what is the box that I have set. So, let me change it to 1 second. I have set it to 2.5 seconds. So, that is why you can see very shortening of the signal, but so if I want to if it looks really not perfect, what I will do is that I will change duration to 1 second, right. So, here we can easily, so one box is 1 second and total we have total 9 boxes, 1 2 3 4 5 6 7 8 9. So, total we have 9 boxes and we will see how many number of peaks that we are getting it. So, in order to understand how many number of peaks that we are getting, let me stop at this point. Oh, okay. Let me run for one more time and I will stop it. I am stopping at this point. Now, if I calculate 1 2 3 4 5 6 7 8 9. So, 9 peaks, 9 heads, 9 peaks and for 9 seconds. So, we have a total of 9 second scale, 9 heads, 60. So, the frequency is somewhere around 60. So, if I want to find out accurately, what we can also do is that rather than taking to 1 second, I will take it as 2.5 seconds. Let me see. So, total 9 boxes, 2.5 into 9. So, 2.5 into 9 is somewhere around 22.5. So, total is of 22.5 seconds, and how many number of peaks we have? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24. So, total we have 24 peaks in a time duration of 22.5 seconds. I need per minute, meaning 60 seconds. So, 60 seconds how many peaks? 60 into 29, 24, sorry, 60 into whatever, how many number of peaks? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24. So, 24 peaks divided by 22.5. So, we are getting somewhere around 64 BPM. So, the average BPM of the subject that we have here is of 64 BPM, which is a normal rate, sorry 64 BPM, which is also a normal rate. So, now it is clear that when we pass a signal through amplifier, it amplifies, but it also it cannot remove anything. but after passing the signal through our pre-processing stage, our filtering and everything, we have seen very pure like meaning we have seen the signals which are filtered output, which was removed by our high pass as well as low pass filtering. So, once we connect the signals to the other stages, even we can see the peak detection, as we have already seen on our practical and experiment of that particular system, and we can also record, we can also visualize the the output peak outputs by using our peak detectors, and we can also set a threshold using our resistor divider circuits. Then since we also have the comparator, it will compare and gives the high peaks too. Since the frequency is really higher, it is very hard to visualize with our LED that we have connected there in the circuit board, but once if it is if we connect it to the CRO, we can see the pulses too. But since we already have oscilloscope here, rather than doing all the analog, since we have also shown how the working of the operational amplifiers in theoretical and the subsystem level as well as in practical session, why don't we understand how digitally we can do it. So, in order to understand how digitally we do it, generally we will take a microprocessor or microcontroller. So, we will connect in the same way. We require to have an amplification, as well as either we can go with a digital filtering or our analog filtering, the way that we use it. Once the pre-processing and amplification pre-processing stage is done, we can pass the signal to our digital system. So, in this case we are using DSO, or we can also go with our microprocessor or microcontroller. Once we acquire, we will get a digital data, and that is a filtered digital data. So, once we do the processing in the processor, how do we have to do the processing? If you recall what we have discussed when we are designing our subsystem, first step is to find out the peak value. How do you calculate the peak value? So, I will compare the first value with the next value as well as preceding value and the next value. If this particular value is greater than this value and this value, I can say this value is peak, right. If you see, the peak will be something like this. This value, the peak value will be always higher compared to the next value, either in the right direction or the left direction, right. So, since our interest was only towards our positive side, I can pass through a low rectifier circuit or half wave rectifier circuit, so that only the peak signals of the positive peaks can only be passed through that, and by using a capacitor I can charge it to the peak value, right. So, whichever the voltage that we are getting, QRS peak amplitude that we are getting, by passing through the capacitor, even I can pass it. After passing it, by using a resistor, I can set a threshold. Now, when we set a threshold, right, the way that we have calculated a frequency, right, we can see how many signals, how many peaks that we are getting after passing through the thresholds. If I can count those many number of peaks by writing an algorithm, right, my problem is solved. Now, that is one way. Or if I see the time duration, so we have seen in frequency domain, we can calculate it manually. Why don't I see in frequency domain? So, in order to understand that, what I will do is that I will take a cursor, I will take two cursors. So, I need time duration cursors. So, one I will connect it at one peak. So, right now I am at connected at this particular peak value, you can see that. I will take one more cursor, cursor 2, and I will connect it another peak, right. So, one I have connected at this peak, other one I have connected at this peak. Now, when I see delta frequency, so we are getting somewhere around 900 milliseconds. The time duration between the first signal to another signal is somewhere around 900 millisecond, okay, which is cursor 1, source 1, cursor 1, okay, cursor 2, okay. Now, what has happened? 360. Okay, I will take these two peaks, one is this peak, good. Then I will take cursor 1, I will take at this point, right. So, when I see the time duration between these two peaks is 960 milliseconds. So, when we calculate 1 divided by 960 milliseconds, it will be somewhere around 1 h. So, even here we can see in the cursor somewhere around 1.042 Hz. So, 1.042 Hz is approximately, when we calculate, it is 64. .02, or we can also say that since we know the frequency which is of 1.042 Hz, I want to know the time duration of each thing. So, it is of 900, right. The distance between both the things is 960 milliseconds. So, I need for 60 seconds. How many number of 62? So, when we calculate it, we get somewhere around 62 the pulses, 62 pulses in 1 minute, right. So, even you can do the digitally, the logic that we have seen, or even we can calculate with our thing. So, but the whole idea is that by using our analog circuitry, we can even acquire the AC signal, we can even do the signal conditioning and the processing to some extent. Of course, we can also make it very pure signal, but we require the complexity of the system will be too huge. So, in order to build first order and second order system, we will be taking so many resistors, capacitors, as well as op amps. If we go with an higher order filters, more number of op amps and more number of circuitry, so that to have a better roll off, we have to always go with an higher order filter, so that the results will be really good, right. So, in this way we can see that the acquisition as well as condition of a signal. So, we will stop at this point. I hope it is clear, and thank you very much.